Right, so for question 1, basically the key information is that you're looking for the atom with the smallest number of neutrons. So the way that's calculated is to work out the number of neutrons, that is the mass number minus the atomic number. Now you'll need your periodic table handy for this. So basically the mass number is indicated in the question, the atomic number will always be on the periodic table. For hydrogen, the mass number is 3 and the atomic number is 1. For helium, your mass number is 4, atomic number 2. Helium 5, mass 5, atomic number of 2. And finally lithium, mass number 4 and 3 protons. So when you do all those quick sums there, you are looking for the atom which has the smallest number of neutrons. Well, in this case that is lithium because it equals 1, and so lithium is your answer. Okay, so when discussing the size of an atom, basically there are two things that you need to discuss. The first of which will be shielding, and secondly the nuclear charge, or the number of protons in the nucleus. Now if you look at all of the atoms that you are given on the left hand side there, you'll notice that they're all in the same period and therefore they all have the same shielding. The only difference as you read through is the number of protons in the nucleus. So basically as you go from left to right across a period, there is more protons, and for that reason, because there's a greater positive charge in the nucleus, it attracts the outer electrons more. That means that the nucleus is pulling the shells in and reducing the size of the atom. Because as you get further to the right of the period, the atoms get smaller, that means the largest atom is at the start of the period and is therefore sodium. Okay, so just to begin with, fairly straightforward question. You're looking at defining the term atomic number. Now, you should all know from the start of atomic structure and from your GCSE that atomic number basically defines the number of protons in the nucleus. And that is what you would have to write down in order to get the mark there. Second question, and basically it's asking why atoms may have different mass numbers. The definition is not just to write that they are isotopes, but that they have different amounts of neutrons. And again, you have to mention the neutrons in order to get the mark. So different amount of neutrons gets you that second mark there. Moving on to the mass spectrometry question. Basically, it says name the instrument here. Everyone hopefully should have known time of flight mass spectrometer is what is used to measure the abundance of isotopes. You could have alternatively just said mass spectrometer and you would have still got the same mark. Question after that is calculating relative atomic mass, and that's the phrase that you're looking for when you've got mass spectrometry data. And this is the standard 2-3 mark question where you use the data in the table above. So you're looking at 82 times 12, which is this column of data here, plus 83 times 12, this column of data, plus 84 times 50, plus 86 times 26. And if you divide all of that by the sum total of parts, which in this case is 100, that will give you the answer. So that's the method for that question there. On to part D, we need to be able to write A-level electron configuration in terms of S, P and D sublevels. This one goes a little bit beyond what you're expected to know from basically all the way up to 3D, and you have to actually go into the 4p orbitals for this one. So what you're looking at is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, remember that it fills before 3D, and it goes back to 3d10, and then finally 4p6. And remember that 4p actually fills after 3D, just because of the energy difference between 4s and 3D. In the next part, wants you to explain why reactions of krypton is unexpected. And as you should all know, krypton is a noble gas, and therefore it's unlikely to form bonds. So that's exactly what you have to write down. Noble gases have a full outer shell and therefore don't form bonds. Lastly, it says, using a suitable model of atomic structure, explain why the following experimental data can be observed. And the first one is that you're looking at the first ionization energy of krypton and bromine. Now, both krypton and bromine are in the same period. However, you need to explain why it's harder to take an electron from krypton than it is from bromine. The reason for this is that krypton has similar shielding, but more protons in the nucleus. And because there's more protons and the outer electron is the same distance away, they get attracted more strongly, and therefore more energy is required to remove the electron. As the attraction is greater. So, I know obviously there's only 2 lines then, that goes a little bit beyond, but that is the level of information you want for those 2 marks there. That same kind of explanation is what you need to put in to part 2 here. Now, part 2 again requires you to discuss both shielding and proton number. But obviously aluminium and magnesium is one of the special cases we learned about during atomic structure. So Al is less than Mg because Al's outer electron is in the 3p orbital, which is slightly further away from the nucleus than the outer electron in magnesium, which is in 3s. So there is greater shielding because it's further away from the nucleus, therefore a lower attraction, and then again therefore it's easier to remove, and that gets you the 2 marks for that one there. Mass is one that you should know. It was brought up as part of the last KAG and you were expected to start to remember that. And basically, the key thing here is that you write that it is the average mass of an atom to begin with, and you're going to compare that to one atom, or 1/12 of an atom of carbon-12. And that there is the 2-mark definition that you have to write down in order to get both of those marks. The thing that a lot of people miss there is the average, so make sure that that's put in there in order to get both marks. Part 2 is exactly the same as the previous question, where you had to calculate the relative atomic mass, but this time it gives you the relative atomic mass and you have to work backwards in order to find the mass of a specific silver atom. In addition to that, it also states that you have to state why the isotopes of silver have identical chemical properties, something again that came up in the last KAG and needed to be recovered. So just to begin with, the reason that they have same or similar identical chemical properties is because they have the same electron configuration. That gets you that mark, and then that's out of the way. The next thing is to do the calculation. Now, what it says in the question is that the relative atomic mass of silver is 107.9. So we've already done the maths, and it's worked it out that it's 107.9. And that equals the 54%, which weighs 107.1, plus the remaining percentage, which in this case is 46, times an unknown, which we'll call m for mass. Okay, and again divided by 100. The key in this question is to be able to rearrange that equation in order to be able to find the relative atomic mass. So if you multiply both sides by 100, you end up with 10790 equals 54 times 107.1 plus 46m. You then multiply out the 54 times 107.1 and you take that from the other side. So 54 lots of 107.1 should give you 5783.4. So 1790 equals 5783.4 plus 46m. You then take 5783.4 from both sides, and that should give you 5006.6. And then finally, to get m on its own, you divide by 46, and you should calculate that m to one decimal place is 108.8. Okay, for the graph drawing question, you were given quite a bit of information. If you have a little look back up, you're given two sections of information. You're given the time of heating in minutes, and you're given the mass of the crucible in grams. The first thing to indicate is that just underneath here, it does tell you that the mass of the crucible and boric acid here is on the y-axis, and you need to make sure that you understand what is the y-axis, and therefore the mass has to be plotted on the x-axis. Sorry, the time has to be plotted on the x-axis. If you go down, have a quick look at the graph that has been drawn. I've plotted the points on here. One thing to make sure that you do, make sure that you show the labels. So I've got mass in grams here on the y-axis, and it's nicely been cut off on the bottom, but you've got time in minutes on the x-axis. Now, the x-axis starts at 0 and runs up to 35 minutes. However, you will notice that on the y-axis, the mass I've written ran from 33 up to 36. Now, it's important that when you draw a graph, you do not use this to show a broken axis. In chemistry, in biology, even in maths, if you use that, it does not allow you to extrapolate data backwards effectively, and therefore you should not do it. So make sure in future that you don't do that. And initially, quite a few people like to start their axis at 0. You do not have to, and in fact it is wrong to start your axis at 0. You should use an appropriate scale that starts just below your minimum value and goes to just above your maximum value in order for you to make the graph as big as possible. On top of that, you need to make sure that you use as much of the graph paper as possible. That allows you to find data out as accurately as possible and to minimize the amount of error you get from your graph drawing. So use as much of the paper as possible, get your scale right, put your labels on, and finally make sure that you draw your line of best fit through the points, and in this case that should have been a curve. Right, so moving on to question 5. This started to assess your knowledge of amount of substance, and the first thing to realise is that it says that you've got the gas constant, and therefore you're looking at PV equals nRT. What the question says is that you want to calculate in volume, in meters cubed, the volume of gaseous phosphorus 5 oxide, and that is P4O10. So that's the oxide that we're looking for. It also starts to give you the temperature and the pressure as well. Before we can do that though, you need to be able to use the mass that is given of phosphorus. Now you've got 220 grams of phosphorus, and we need to work out the number of moles. So as always, you're going to make a table, P4, and we're going to have mass, MR, moles, and ratio down the side. Now, Mass is quite easy, obviously, it's given in the question, 220 grams. However, a lot of people got the MR wrong because phosphorus has the formula P4, and you can see that is given in the equation here. So a lot of people made a couple of mistakes here. P4, phosphorus has a relative atomic mass of, and you'll need a periodic table just to check it. Phosphorus has a relative atomic mass of 31. So to get its molecular mass, you do 31 times 4, which is 124. To get the moles, remember that it is mass, MR, and moles. So to calculate moles, it's mass divided by MR. So you're going to do 220 divided by 124. That gives you the moles, which is 1.77. The ratio between phosphorus and phosphorus 5 oxide is 1 to 1, and therefore we also have 1.77 moles of P4O10. That's the first part. We then need to start doing PV equals nRT. Just to quickly drop back, we know that we've got 1.77 moles. And we need to start using P, V, N, R, and T. So we've got 1.77 here. Our pressure is 101 kilopascals. Remember that you do need to be able to convert it. So that becomes 101,000 pascals. Volume is our unknown, X. R is given to you in the question, is 8.31. And the temperature needs to be in Kelvin. Now remember that is adding 273 on. So the temperature becomes 773. What we then need to be able to do is to rearrange the equation in order to calculate V. Remember that the equation is PV equals nRT, and therefore to calculate V it becomes nRT over P. And so in this case we're going to do 1.77 times 8.31 times 773, all divided by 101,000, and that should give us our answer. And in this case, the answer is 0.113 meters cubed. Moving on to the next question. In this one we have to calculate the mass of phosphoric acid and link it to a certain volume and concentration. So initially, remember, phosphorus 5 oxide is P4O10, and we need to work out its mass. Phosphoric acid is this one here, H3PO4. So again we're going to make a table, P4O10. Because we need to work out the mass, we're going to put mass, MR, moles, and ratio. And down the other side, we want phosphoric acid, H3PO4, with volume, concentration, moles, and ratio. Before we fill anything in, we're going to try and give as much information from the question before we do any calculations. The first thing to note is that the volume is 3 meters cubed. Now, normally we want volume in decimeters cubed, so to convert from meters cubed to decimeters cubed, you multiply by 1,000, which means that we have 3,000 decimeters cubed, which is obviously quite large, and so therefore you're expecting large numbers at the end. Concentration is 5, and therefore to get moles, you multiply those two together, and you end up with 15,000 moles. Information in the question tells us that it is a 4:1 ratio, and therefore you have to divide by 4 in order to get the moles of phosphorus 5 oxide. So your moles here should be 3,750. The MR of phosphorus 5 oxide, obviously phosphorus, remember, is 31, so 31 times 4 plus 160, which is 10 times 16. That gives you an MR of 284, and therefore if you multiply moles and MR together, that should give you mass. And the mass that you should get is 1065000 grams. Now, you can leave it as that. However, a lot of you did convert to kilograms and told me that you had 1065 kilograms or 1.065 tons. Either of those, well, any of those three answers would be correct in the exam. Part C, again, very similar question related to the phosphoric acid that we've been producing all the way through. In this case, it's wanting you to calculate the percentage yield. And before we even get started, it's worth noting down the percentage yield calculation. So that is that percentage yield equals the actual mass divided by the theoretical mass times 100. We can work from there, and we're told that your actual mass that is produced during the reaction is 1.09 kilograms. So feel free to either convert that into to grams or leave it as kilograms. I prefer to convert and leave it as 1090, and we have to work out the theoretical mass that can be produced. Now, at the start of the question, we are told that 3.5 kilograms of calcium phosphate is added to an excess of aqueous sulfuric acid. So we're only going to be using the calcium phosphate numbers, and therefore we're going to set up a table. Calcium phosphate, Ca3PO4 and again, because we've got a mass, it's mass, MR, moles, and ratio. And on the other side of it, we're going to be looking at phosphoric acid, which is H3PO4. And again, it's looking at a mass, so we're going to leave it as mass, MR, moles, and ratio. Again, just to begin with, we can put 3,500 grams in at the start. The MR is calculated by having 3 calciums. Calcium has a molecular mass, an atomic mass of 40.1. So you've got 3 lots of that, plus 2 phosphoruses. Both have a relative atomic mass of 31, and 8 oxygens. So 8 lots of 16. That gives you a total relative atomic mass of 310.3. To get moles, you divide the two numbers that you've got, so it's 3,500 divided by 310.3. That gives you a total moles of 11.28. The ratio between the two is 1 to 2. You get that from the equation at the top. And therefore the moles of phosphoric acid is 22.56. The MR of phosphoric acid, so you've got 3 hydrogens, that's 3 plus 31 for the phosphorus, plus 4 lots of 16, tells you that you've got an MR of 98, and when you multiply those two numbers together, you end up with 2,210.9 grams. That is the actual, the theoretical mass that you could produce, the maximum mass possible, and therefore that goes in on the bottom line. And then if you can use those bits of information there to calculate the percentage yield, and the percentage yield comes out as 49.3%. Finally, explaining which method has the greatest atom economy. So you have to look back at the two equations. Firstly, this equation here has 5 products. So 3 of the molecules that produces products are waste products, so it's not very efficient. If you compare that back to this equation here, where there's only a single product, there's 4 molecules produced, but they're all the desired product, anything with only 1 product at the end of it has 100% efficiency. And therefore, you could say that the first equation has the highest atom economy, as there is only one product. And again, that gets you that mark. Right, this is a real application question. It's something really different, something you've never seen before, but linked back into something that you already know. The first thing to note is that you have this copper, well, it's a basic copper carbonate, and it includes the alkali ion OH- and the carbonate ion CO3 2-. First thing to note down is this is asking you what different reactions can take place when you add an acid to both an alkali and also to a carbonate. When you do this reaction, the Cu2OH2CO3 reacts with HCl in order to form a salt and water when the hydrochloric acid reacts with the base, the alkali. So you're going to get copper chloride, CuCl2, and you're also going to get H2O as a product. But when an acid reacts with a carbonate, you get a salt, water, and carbon dioxide. So you're also going to get CO2 produced. You get 1 mark just for writing that equation and not balancing it. Beyond that, you do need to include the balancing in the equation. The first thing to note is that there are 2 coppers, and therefore you have to produce 2 copper chlorides. That in turn makes you have 4 chlorine atoms on the right hand side, and for that reason you need 4 HCl's on the left. And then finally you need to make sure that the oxygens are balanced and the hydrogens are balanced. The only thing on the right hand side containing hydrogen is water. So in total you have 6 hydrogens, and therefore you have to have 3 waters. That there is the balanced equation for the reaction, and that's what gets you 2 marks. When it comes to the next question, it says suggest one observation that could be made. Typical response here often ignored the observation and just stated what is produced. Because carbon dioxide is produced during the reaction, what that means is that you will see bubbles of gas being produced. You can either write that as effervescence, or alternatively, if you just write the term bubbles, that will get you that additional mark. After that, it goes on to an empirical formula question, and just before any of the data is required to be used, it says state what is meant by the term empirical formula. This was badly answered because a lot of people didn't state exactly what it means, and it is the simplest ratio of atoms in a molecule. And that there is the exact information required in order to calculate the empirical formula, and that gets you that first mark. The second bit asks you to calculate the empirical formula, and the big thing a lot of people missed is that the copper carbonate has copper atoms in it. So to start off with, you're given values for the mass of carbon, the mass of hydrogen, the mass of hydrogen there, and also the mass of oxygen, but you're not given the information for the mass of copper. So in order to do that, the maths you have to do is you're told that it's got 5 grams of the sample. You know that 0.348 of those 5 grams is carbon, 0.029 of those 5 grams is hydrogen, and finally 1.858 grams is oxygen. And therefore your mass of copper comes out as 2.765. So that's the starting point. After that, what you need to be able to do is to produce a table, and remember that empirical formula is just an application of moles equals mass over mR, and we have copper, we have carbon, we have hydrogen, and we have oxygen. And we've got mass, mR, moles, and ratio. So copper is 2.77 grams. Carbon, as we've already seen, above is 0.348 grams. hydrogen is 0.029 grams, and oxygen is the remainder, which is 1.858. You're going to then use your periodic table to work out the atomic mass of each. The final three should be easy. Carbon you should know is 12, hydrogen 1 and oxygen 16. Copper you will have to look up, which is 63.5. And then you're just going to divide each set of numbers in order to calculate the moles. So for copper, if you divide those two, what you should end up with is 0.044. Carbon, 0.348 divided by 12 should get you 0.029. Hydrogen is also 0.029. And then oxygen is 0.12. So you can see those different moles there, and then we have to turn it into a ratio. So the easiest way to do that is to divide each of the four numbers by the smallest out of the four. In this case, this is either carbon or hydrogen, both of which are 0.029. So therefore, you get one of those. 0.044 divided by 0.029 gets you a 1.5 ratio, and then finally oxygen gets you 4.1, so approximately 4. Because we're not allowed to have a 0.5 of an atom, can't exist that you can get half an atom, we need to multiply it up. So the easiest way to get 1.5 up to a whole number is to multiply by 2, and therefore you get 3 to 2 to 2 to 8. And that is the empirical formula, or the empirical ratio of the atoms, and therefore the empirical formula is Cu3, C2, H2, O8. And that gets you all 3 marks. Okay, so last question in the paper. It's all to do with titrations. It's to do with the titration that you were doing as part of your practical assignments over the last couple of weeks. And to begin with, what it asks you to do is to calculate the mean titer value. Remember that this is only done by taking into account the concordant results. And if you have a look in the table, the two titer values that are concordant or within 0.1 of each other are 9.75 and 9.65. The rest are more than 0.1 out, and therefore you can't take them into account when you take your average. So, to calculate the mean titer value, I'm going to find the calculator. You're going to do 9.75 plus 9.65 divided by 2, which is 9.60. So that's the first thing to identify, that is the mean titer value when it comes to this question. It then asks us to use that value in order to calculate the moles of HCl that react with 25 centimetre cubed of the MHCO3 solution. So all you're looking for in this case is the moles of HCl, and we're going to do concentrate. So for HCl, concentration, volume, moles. We don't need ratio. The concentration is given to you in the question. The concentration is 0.12, and therefore we can use that in the table below. So 0.102. The volume, as we've just worked out, is 9.6 centimetres cubed, which when converted to decimeters cubed and divided by 1,000 is 0.0096. A lot of people forget that conversion when it comes to the calculation, so make sure you do it, and then you multiply it by 0.102, and that gives you an answer for the moles of 0.0000979, or just 98. So that's the first question there. Moving on to the next part, what it wants us to do is to calculate the amount in moles of MHCO3 and 250 centimeters cubed of the solution. The first thing to do here is to identify that it's a 1-to-1 ratio because of the information that we're given in the equation. So it's a 1-to-1 ratio between MHCO3 and HCl, so we don't have to multiply for a mole ratio. All we have to do is to use the volume. Now it tells us that this moles that we calculated in the previous part is what reacted with 25 centimeter cubed of MHCO3. So in 250 centimeters cubed we've got 10 times that. So in order to start the question, you take your 0.00098 and multiply by 10 in order to get 0.0098 moles of MHCO3, and that's in 250 centimeters cubed. What it then asks us to do is to calculate the MR. So for MHCO3 we have mass, MR, moles, and we can ignore ratio because we're not doing a reaction. We've got 0.0098 and the mass is given to us in the question. If you have a look back at the top, it does tell us, and you do have to convert, that we've got 1,464 milligrams, which when you convert into grams is 1.464. To get the MR, remember that it is mass, MR and moles. That's the triangle there. So when you come to rearrange it, in order to find MR, you're going to do mass divided by moles. So in this case that is 1.464 divided by 0.0098, and you get 149.4 as your MR. It doesn't require you to do any more than that, but remember, to finish the question off, it does ask you to give your answer to the appropriate number of significant figures, and in this case all of the values in the question, if you have a little look back, were given to 3 significant figures, and therefore you can only give your answer to 3 significant figures, and in that case your answer should be 149. The next question posed a little bit of a problem. I didn't see anyone get this right, and the key part of this is that it says using the same apparatus suggests how a procedure could be improved to reduce percentage uncertainty. Now, this is a maths problem, but without you having to use any maths in particular. Remember that the percentage uncertainty for a piece of apparatus is the error divided by the minimum value measured times 100, and for that reason we need to alter the values in that equation in order to minimize the percentage uncertainty. So because we're using the same apparatus, the error on that piece of apparatus will not change. The only other value that can change is the minimum value measured. So you want to increase the value measured in order to minimize the percentage uncertainty, because a bigger value on the bottom of that fraction will make the fraction smaller. So the suggestion is to use a greater volume of hydrochloric acid, because that in itself will reduce the percentage uncertainty. Your justification for doing that is, well, effectively, or the way of doing that is to either lower the concentration of HCl. That will mean you'll have to use more of it in order to neutralize the MHCO3, or alternatively you want to increase the concentration of MHCO3, which would require more of the same concentration hydrochloric acid in order to neutralize it. So either of those two things here as individual points would get you that second mark, but the first mark is for using a greater volume of hydrochloric acid. And I think most people, having seen that question now, should be able to answer it effectively. Last one, is exactly what we've experienced over the last few lessons, being able to write a 6 marker based around producing a volumetric solution of 250 centimeters cubed containing MHCO3. A lot of people, where they made the mistakes was to do with making reference to the different equipment that they were using, often referring to conical flasks rather than volumetric flasks, etc. So we'll just talk through it, make sure you've got the points. But the first thing is that you're going to zero the balance, and then you're going to weigh out the MHCO3, however much that is. It doesn't tell you how much is there, so you can just say that you weigh out the MHCO3. Then you're going to pre-dissolve in distilled water and transfer to a 250 centimeter cubed volumetric flask. Now, again, make sure you reference the volume of the volumetric flask. Make sure that you call it a volumetric flask, because both of those things are important in order to get a mark. The next thing that you need to do is to wash the weighing boat into the volumetric flask. That makes sure that all of the solid is transferred across and that you don't lose any during the transfer process. Once you've done that, you're going to swirl until dissolved, and then add distilled water until the meniscus lies on the 250 centimeter cubed line. That makes sure you've got the right volume in there. Finally, you're going to stop where the bottle and invert to ensure it's fully mixed. That in itself there will get you 6 marks, and most people did put all of that information in. However, some of it was missed out in terms of the details about the volumetric flask, but most of it was generally done really well.